Today we're going to use exponential and logarithmic functions from Module 8, Lesson 5 of Algebra 2. And we need equations or formulas, I would say. And so we had this one previously down here called the continuously compounded interest. And today they're just going to manipulate that a little bit, call it continuous exponential growth. And so this formula is what you need, and it's fully explained down here. Now, first thing I would like to say is these two formulas are the same. Right? It's just that P is principal, interest rate. So this applies to money. Right? This we can apply to more situations. Right? Your variables, your true variables, are the y. The y obviously changes, and time changes. All right. So y changes as a variation of time, and so you will always need an a. You always need an initial amount, and you will always need a k, a rate, right, of continuous growth. The big difference is between this unit or lesson right now and what we've done in previous lessons is that they are not going to provide you the rate to start out. And so questions end up getting a little bit long, but we're not going to do very many of them. But let's look at two examples. First example, in 2016, the population of Florida was 20.61 million people. In 2000, it was 15.98 million people. This is write an exponential growth equation. Again, from the last slide, that means I need to write an equation in the form like this. And I have to have an a and I have to have a k. All right. So what is the a? What is the initial amount for this problem? What is the initial amount? Hopefully you agree with me that the initial amount is 15.98. They're starting in the year 2000, 15.98 million. And what is the k? What is the rate? Is there a rate? I don't see a rate. And so that's the first thing we need to find is the rate. So we're going to switch slides here and just go to find the rate. And so I'm going to plug in the y, the new amount, which the newest amount they gave me was 20.61 million. Equals the initial amount times E, and I don't know what K is, but I know the difference between those two amounts is 16 years because they said it was 2016 from 2000. And now I'm going to divide both sides by 15.98. I'm going to rewrite instead of K16. I just like it better as looking like it's 16K. And now I don't want the variable pi, that K, I want to bring that back down to the equation. So right now it's an exponent. It's way up there. Bad K, get down K. How do I bring it down? And that's by logging both sides. Now when I log and it is an E, I have to do the natural log, so I ln both sides. And so essentially at this point I have ln of all of that, 20.61 over 15.98 equals, well, ln E cancel out, so just 16K. And so now I'm going to divide both sides by 16. So I have ln 20.61 over 15.98 divided by 16 equals K. And so you plug that in to the calculator. You'll probably end up rounding. And I got K as 0.0159. Now when you type that into a calculator, you do ln and then 20.61 divided by 15.98. And you probably need to close the parentheses and then divide by 16. Or do them as two separate parts. Do the whole top and then divide by 16.
Just to remind your students, if you are signed up to take the...
Sorry about that interruption. K is, again, from the calculator, 0.0159. And as for the whole equation, and so I'm going to write my final answer here as y equals 15.98 E 0.0159. 0.159t. So that whole equation is my exponential growth equation, and that is what I'm going to use for part B. Part B, they're asking me predict when the population will reach 25 million. And remember, we just got y equals 15.98 e 0.0159 t. Right? And so to predict when it will reach 25 million, I got to plug 25 in and figure out how many years that'll be. And again, I divide by 15.98. And again, I have a variable that's up as an exponent. And so to bring that down, I have to ln both sides. And so I end up with ln 25 divided by 15.98 equals, those two cancel out, so just 0.0159t. To get t by itself, I have to divide by 0.0159, and so I have ln 25 over 15.98, whole thing, divided by 0.0159 equals t. And when I did it, I got 28 something, 28 and change. So around 28 years is how long it's going to take. And if we started in year 2000, then I just put my answer as around 2028. Different formula here if it's declining, if it's getting smaller. And we're going to stay with the more standard or basic example of a half-life. All right, half-life is from science class. Hopefully you've learned that at some point in science class. It's the time it takes something to cut in half. And it works really well because our new amount is half and our initial amount is a whole. So that makes the math of this a little bit easier than the ones we just did. Notice that this formula is the exact same, except for the k is a negative. And so this example here says the half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. The radioactive substance thorium-230 is used to determine the age of caves, formations, and coral. The half-life of thorium-230 is 75,381 years. It lives a long time. Determine the value of K in the equation of decay for thorium-230, and how much of a 2-gram sample of thorium-230 should be left after 1,500 years. A lot there. Let's chunk it out. What are we talking about? We're talking about thorium-230. What do we know about thorium-230? It has a half-life, 75,381 years. What's the first thing I'm trying to do? I'm trying to find K. And so, again, I got to remember what we just had on the previous slide, that the equation is initial amount and then negative k to the power of t. Again, I need a and k. I don't have a k. I'm trying to find k. The new amount is half. So the new amount is half. Let's just put 0.5.
Good morning, Fort here in Northern. I'm Camille Keys.
And so the new amount is a half of the whole. So the initial amount, I can put a 1 there because it starts as a whole and then it halves. I don't know k. And the t is the half-life, so it's 5,381 years. I don't need, because it's 1 times anything is itself, I don't need to put that 1 there. And so to get rid of the e, I have to, or to bring the k down, I guess, really, to bring the k down, I have to ln both sides. And so I have ln 0.5 equals, And I'm going to just write this as negative 75,381. Okay. And so then I have to divide both sides to get k by itself. So I have ln 0.5 divided by negative 75,381 equals k. And so it just asked me to find k. And if you do that on a calculator, it might have a struggle bus. It might tell you something like it's 9.19 times 10 to the negative 6, or it might say e to the negative 6. And that means that we have to move this decimal place. All right. And so I'm going to put 0.0000005 zeros and then 9, 2. I'm going to round it to 2. Right. So first up, find k. I found k. It's that small number. Right. So now I need to know how much of a 2 gram. So how much? I don't know. That's the question. I don't know what the new amount's going to be. I know I started with 2 grams. I know my rate is always negative in decay, 0.00000092, right? And then the t they told me was right there, 1,500 years. And you just use a calculator. You type that into a calculator. Very carefully, you type into a calculator, you get that it takes approximately, it would be, well, how much would be left? Of the 2 grams, how much would be left? It's approximately 1.97 grams. Again, it was a huge half-life, 75,000 years, so 1,500 years isn't going to affect it very much. And there's something to try. That's what we're doing in my class. Thanks for watching. Have a great day.